So you look around the room, you see things. Your brain isn't just getting a picture of shapes and lines, it's getting a world filled with color, a peculiarity of vision that helps you differentiate all of the stuff you're seeing. And that seems straightforward enough. But now comes an intriguing question to your mind. How many different colors can a person's eyes actually tell apart? You'd think the answer would be pretty much the same for everyone, but it's not. Not even close. You see, for most of us, we see the world through 3 types of tiny light detectors, 3 different types of cone cells in the back of our eyes. Think of it like having 3 sliders for mixing paint, 1 for long wavelengths, 1 for medium wavelengths, and 1 for short wavelengths, generally associated with red, green, and blue respectively in an additive color context. By adjusting these 3 sliders, you can create all the colors you know. That's trichromacy, and it's the standard human setup. Some people only have 2 working sliders, or their 3rd slider is only partially working. These people have a color vision deficiency and they see fewer colors than the rest of us. But here's where it gets really interesting. If one less cone type results in measurably fewer colors, what does the opposite do? What if someone had a 4th slider thanks to a 4th type of cone cell? A very small number of people, it turns out, do. They're called tetrachromats. And the result is, well, it's not just a few new colors in tetrachromacy. Rather, tetrachromats can see an additional dimension of color, literally. They can distinguish way more than 100 times more colors than the rest of us. In a digital color context, this is about 4 billion tetrachromatic colors, instead of the normal 16 million trichromatic colors. Now, how in the world does adding just 1 more type of cone cell in the eye lead to such a ridiculous exponential explosion of color? You'd think the answer must be some fantastically complicated biology, but it's not. It's actually some wonderfully simple, elegant math. A little quirk of how dimensions work. It's all about what happens when you add 1 more dimension to a system. That's what we are going to explore in this video, in the applied context of color vision. We are going to see how a simple quirk of dimensional math, just adding 1 more axis to the trichromatic color space, transforms the visual world of a tetrachromat into something so magnificently colorful that normal trichromats seem colorblind in comparison. By necessity, and to make this topic a lot more visually interesting, we'll even functionally simulate tetrachromatic colors through an entirely new type of color that I've invented. So stay with me as I'm about to blow your mind with colors and visualizations that you've never seen before. Color vision is deeply connected with math. Specifically, it is dimensional math that makes the relatively simple mechanism behind our color vision so very effective. I hope that I'm not discriminating with the following assumption, but as a 3-dimensional being, you should already be familiar with how dimensions and dimensional math work. As a recap, dimensional math involves understanding how many independent parameters are needed to specify a location within a given space. It's fundamentally about the number of dimensions, which can be visualized as the number of axes needed to define that location. Basically, for each dimension, you're adding 1 new dynamic range of values that can be independently adjusted to specify the location of something in space. Here, the definition of space is intentionally vague because it doesn't have to be an actual physical space, although it can always be rendered as such. A space can also be virtual and conceptual. In our familiar spatial dimensions, this means that in 0 dimensions, space is a point. In a single dimension, space is a line. In 2 dimensions, space is a plane. In 3 dimensions, space is a solid shape like a cube, and in 4 dimensions, space surpasses 3-dimensional limitations and expands into a 4th spatial dimension orthogonal to the previous 3, for example in the form of a hypercube. Although each time we are merely adding a single range of values to the mix, this simple change results in an incredible number of new and unique possible locations in the expanded space. Mathematically speaking, what separates us 3-dimensional beings from 2-dimensional beings only is a single value range, which can sound a little bit scary. But this characteristic is also the catalyst for how tetrachromacy becomes so much more colorful than trichromacy. Dimensionally, color vision works identical to how spatial dimensions scale with each additional axis. The space of color is much more virtual and conceptual though, but since it's the same math as in spatial dimensions, you can also spatially visualize colors. To begin with, we can see colors because of a certain type of cell in the back of our eyes. These are called cones. They are located in our eye's retina and are arranged in a mosaic pattern. Hence, that part of the eye is called the cone mosaic. Most people have 3 types of cones. Each type introduces a new dimension of color and is sensitive to a different yet partially overlapping part of the electromagnetic spectrum. Here we can visualize such a color dimension as a line going from black to that cone type's fully saturated and bright color quality. However, this line is basically just a uniquely identifiable range of values to which the brain assigns the experience of color to make visual perception more intuitive. Naturally, if you have no cone type, you are basically blind, since you need at least a single type of cone to detect light. Here, the color space is 0-dimensional and the only color you can see is black, nothing else. It starts to become a little bit more interesting with a single cone type, though it's still very limited. Here, the color space is 1-dimensional and there's only a line going from black to perceptual white. Taking digital color values as a baseline, it's just a single axis with values ranging from 0 to 255. You can see colors with this monochromatic vision, however, there's no experience of hue yet. Everything's either black, gray or white. With 2 cone types, the concept of hue is being introduced. Hue is a quality of color that allows us to intuitively disassemble various combinations of wavelengths to see which cone types are being stimulated the most and to which relative extent. Therefore, hue is an imbalance in the relative activation of the existing cone types. This aspect of color vision is comparable, although not identical, to how you can use a Fourier transform to decompose complex interwoven sound waves, for example. The Fourier transform is a mathematical tool that breaks down a complex signal into the simple pure frequencies that make it up. Color vision works similarly, but it's fundamentally imperfect in this regard, while still being sufficiently effective for how simple it is. In a perfect Fourier transform of a complex light signal, the virtual color space would effectively be infinitely dimensional, but a dichromat, for example, someone who only has 2 cone types, can only unmix any complex combination of wavelengths of light based on 2 cone types, meaning they can only ever decompose a complex signal into 2 distinct values, that is 2 axes that together form a planar, 2-dimensional color space. The hue subspace of each color vision dimension is always 2 dimensions lower than the main color space. This means that hue in dichromacy is 0-dimensional, so there are just 2 singular hue points that are connected by white, gray and black. With 3 cone types, the color display starts to look more familiar to most of you. Now there's a third color dimension that not only expands the color space to 3 dimensions, but also dimensionally increases the concept of hue to a circle of distinct hues instead of the previous 2 hue points. Notably, it's only the concept of hue that increases dimensionally with each additional cone type. Other color concepts like saturation and luminance only adjust indirectly relative to hue. While in trichromacy there's an additional dimension to hue compared to dichromacy, both saturation and luminance still conceptually remain 1-dimensional throughout all color vision dimensions. Now, with these basics out of the way, we are well prepared to understand tetrachromacy. The main change in tetrachromacy is deceptively simple. We are just adding a new cone type to the eye's retina that detects a different range of wavelengths than the other cone types and evokes a distinct color quality. Just like before, this means we are adding a single and unique range of values to the mix. This seemingly simple change has a massive impact on color discriminability, because through this, tetrachromacy becomes dimensionally more colorful than trichromacy. A functional tetrachromat cannot just see a single new color, rather they can see all trichromatic colors plus a linear extension of all of these trichromatic colors into a 4th color dimension by gradually converging towards the 4th cone type's color. Using digital color values as a baseline, this means that for each color that a normal trichromat can see, a tetrachromat can see 255 additional variations of that color. Doing the math, this means that while a trichromat can distinguish about 16 million colors, a tetrachromat can already distinguish 4 billion colors. These numbers are a bit optimistic, but this exponential increase upholds, no matter which baseline values you're using. But we're getting a little bit ahead of ourselves here. Understanding the math behind tetrachromacy is important. However, my main goal is to visualize this dimensional math of tetrachromacy with actual tetrachromatic colors so that you can intuitively understand tetrachromacy, just like we can intuitively understand trichromacy and its three-dimensional color space through trichromatic colors. For this endeavor, we need to find a method that somehow functionally simulates tetrachromatic colors. In most of my previous videos, I've used so-called Dichoptic colors to functionally simulate tetrachromatic colors. These are normally impossible binocular color combinations of normal trichromatic colors that are generated by disrupting the chromatic redundancy of binocular color vision. We have two eyes and each sees colors independently. When each eye sees a different color for the same object, you can train your brain to combine these two overlapping colors to create a new color experience, and that without the need of a new retinal cone type that introduces an entirely novel primary color quality. This method is incredibly functional once you've gone through enough training. It's basically a cheat code that can transform binocular trichromatic vision towards a functional form of tetrachromacy. All we need to do is to design technology that intelligently disrupts this chromatic redundancy of binocular color vision. The good news is that I've already invented such technology in the form of glasses with a special lens pair called the True Red Tetrachromacy glasses. One lens isolates all deep reddish wavelengths above roughly 630 nanometers in the first eye, and the second lens isolates all the other wavelengths below roughly 630 nanometers in the second eye. This seemingly simple binocular separation generates a functional form of tetrachromacy for trained binocular trichromats. With these true red tetrachromacy glasses, one of your eyes can still see colors trichromatically, but its color vision has become mildly protanopic, meaning it's missing some longer or true red wavelengths. But your second eye reintroduces only these true red wavelengths as a new color dimension, since each eye acts independently before its color signals reach the brain. This means you now have a partial L cone type for very long wavelengths in one eye, which we will call the L plus cone, and another partial L cone type with a similar yet distinct color quality but a totally different lower wavelength detection range in the second eye, which we will call the L minus cone. Although both of these virtual L cone types have a similar primary color quality when isolated, due to the unique dichoptic combination of the L plus cone signal of the true red isolated eye with the S, M and L minus cone signals of the second anomalous trichromatic eye, you can effectively tell apart colors tetrachromatically through these normally impossible color combinations. However, the true red glasses alone are not enough to make you a functional tetrachromat yet. They are a necessary requirement, but you also have to train your eyes and brain to functionally distinguish these dichoptic colors from normal colors. This training can take a lot of time, since most people don't have any experience with these novel dichoptic color experiences yet. So, preferably, we need to find another method that can functionally simulate these higher dimensional true red tetrachromatic colors, a method that works for almost everyone without the need of any prior training. Finding such a method that doesn't need any pre-requirements has been very difficult, but I've managed to invent a new type of color that allows everyone to see a surprisingly functional simulation of the true red tetrachromatic colors that the true red tetrachromacy classes evoke. I've named the following type of color Interlaced Colors, and you'll see why. To understand this new type of color, you have to remember that color is created in context. Every color in a visual scene has an influence on each other. Sometimes this influence is small, and sometimes it's very noticeable. Especially when colors are put directly next to each other in small patterns, you can start to see that colors can even collapse into a totally different color under the influence of each other. For example, if there's a big red square next to a big green square, both colors elevate each other due to their contrast. However, if it's a very small, tightly packed and uniform pattern of red and green squares, both colors collapse into a single yellowish color. Although there's no actual singular wavelength present that evokes a yellowish color experience for trichromats. So when colors are sufficiently big and separated, they reinforce each other. But when they are arranged in a uniformly and small enough pattern, they collapse into their additive or subtractive color mix. This behavior of color is predictable. Now comes the interesting part. Since this mutual color influence exists on a spectrum, there has to be a sweet spot of spatial adjacency where two colors are so close to each other that they positively reinforce each other, but still far enough away from each other that they don't collapse into their color mix. This sweet spot can be narrow, and there are a lot of aspects you have to consider. First of all, the viewing distance needs to be fixed, because the further away you are from an interlaced color, the smaller it becomes relative to you until its component colors eventually collapse. A very close viewing distance is also not optimal, because here the colors gradually leave the sweet spot of spatial adjacency, although they can still kind of work at such a close distance. Furthermore, in the case of this video, you have to watch it in 4K resolution and in full screen on a standard PC monitor, because of YouTube's video compression and the downsizing of a smaller video display. The recommended distance is roughly an arm's length away from your monitor, plus or minus a few decimeters. Lastly and most importantly, we have to consider which pattern we're using to spatially allocate the two component colors. This pattern that's encoded in a so-called texture map cannot be too uniform, because uniformity unfortunately leads to a quicker collapse of the component colors of an interlaced color. But it also cannot be too chaotic, because more chaos results in less spatial resolution. That is worse visual acuity and a loss of detail. I've spent a lot of time searching for the perfect texture map that combines uniformity and chaos in such a way that both spatial resolution is preserved and color collapse is prevented as much as possible. The currently best texture map that I've created looks like this. Here, the interlaced colors components are easily discernible. They're close enough together that they can count towards a single color experience, and they don't collapse into their color mix, while also maintaining sufficient influence on each other. Here, spatial resolution, although slightly impaired, is still good enough that you can discern most small and important details. This makes interlaced colors a completely new type of color that combines both texture and color into a single concept. The important part here is that although we are using a texture to spatially allocate two colors, color itself remains the sole determinant for color identification. We are not cheating by correlating distinct patterns with specific color categories, for example. Rather, it is always color that's being used to identify the color of an object. This might sound trivial, but this aspect of interlaced colors is critical, because it makes them feel like actual colors, instead of merely patterns that have been overlaid on top of colors. To demonstrate that interlaced colors are actually functional, let's take the plane of red deficient dichromatic colors that you can see here, and gradually transform this two-dimensional dichromatic color space into the two-dimensional hue saturation subspace of trichromacy by smoothly adding a red color dimension to the green and blue mixes through interlaced colors. As you can see, although this new trichromatic hue saturation plane starts to look like the trichromatic colors you are familiar with, there's no actual yellow, magenta or white here, for example. And thanks to the unique way interlaced colors are constructed, you can additionally differentiate these trichromatic interlaced colors from normal trichromatic colors. Now that we understand interlaced colors, we can use them to functionally simulate true red tetrachromatic colors. Unlike in biologically inherited retinal tetrachromacy, In true red non-retinal tetrachromacy, there's no entirely novel fourth primary color quality, but rather a second kind of red. The second red, which we will call true red from now on, can independently mix with any other trichromatic color. The result is unconventional combinations of normal colors that are distinct from normal trichromatic colors. For this reason, when using interlaced colors to simulate these normally dichoptic true red tetrachromatic colors, we can simply make the first component of the interlaced color three-dimensional by allowing all trichromatic colors, and will make the second component one-dimensional by restricting its colors to a single range of values corresponding to a second red color dimension, which represents the true red color dimension and goes linearly from black to bright and saturated red. Interlaced true red tetrachromatic colors can look eerily similar to dichoptic true red tetrachromatic colors, which is why I'm using them for this purpose. Of course, both are still different, but in terms of functionality and color quality, interlaced colors are really close to real dichoptic colors. When comparing a section of the retina of a normal trichromat with a section of the virtual retina of a true red tetrachromat, you can see that there's a big difference. As a true red tetrachromat, my cone mosaic is populated by a virtual fourth cone type in a binocular context. In these simplified and normalized cone curve systems that show the normalized response spectra of trichromatic and true red tetrachromatic cones to monochromatic spectral stimuli, you can see how much true red tetrachromacy differs from normal trichromacy. Even when compared to the most likely and functional retinal tetrachromacy, you can see that true red tetrachromacy stands out because its virtual fourth cone type is much better separated, which makes it more functional. Depicting it another way, here you can see which cone type corresponds to which eye. The cone types colored in greenish inhabit the first eye and form the first component color, and the cone type colored purplish inhabits the second eye and forms the second component color. Similar to how we previously transformed the dichromatic color plane into the trichromatic chromaticity plane, with the help of interlaced colors, we can now transform the trichromatic color solid into the tetrachromatic chromaticity solid. To start simple, we can simulate the main hue categories of true red tetrachromacy through interlaced colors by simply counting the unique and complete single and combinatory cone type activations of these four cone types. Remember that hue is an imbalance of cone type activations. For a color to count as a distinct saturated and bright hue, two conditions have to be met. First, at least one cone type needs to be deactivated at all times, and second, at least one cone type needs to be fully activated at all times. We can start by counting all the integer standard trichromatic cone type combinations by temporarily excluding the L+ cone. We can have black, blue, black, green and black, red as single cone activations, black, cyan, black, yellow and black, magenta as two-fold cone activations, plus trichromatic black, white, as well as pure black. You can see that all of these colors are missing the true red component, because for each the second component color is black. This results in 8 trichromatic main color categories if we include black and white. If you now reintroduce the L+ cone type and all its possible combinations with the other 3 cone types, this amount of color categories doubles, because every previously trichromatic color category can now also have a true red component instead of black. This means we additionally have true red-black as a single cone activation, true red-blue, true red-green, true red-red as two-fold cone activations, but also true red-yellow, true red-cyan and true red-magenta as novel unique three-fold cone activations, plus the previously perceptually trichromatic black-white becoming a hue. And lastly, there's the new perceptual white, which now is a true red-white color. This makes 16 unique color categories, and 14 of them are unique hue categories. However, these are only the main hue categories. Just like there are hues between red and yellow in trichromacy, for example, there are also many unique intermediate hues between these 14 distinct hue categories. Now comes the time where the dimensional math visualizations from the beginning of this video become useful, because the space of color vision scales dimensionally identically to spatial dimensions. Of course, I cannot show you the entirety of an actual 4-dimensional tetrachromatic color space on a 2-dimensional screen. However, what I can show you is its hue subspace by using interlaced colors. This hue subspace can be rendered as an opaque sphere. Every point on the surface of this sphere is populated by a unique hue, not just a trichromatic color, but an actual tetrachromatic hue experience. Each of these 2-dimensional hues can vary in both the dimensions of saturation and luminance. If you look closely, you should be able to find each of the aforementioned main hue categories of true red tetrachromacy, as well as all the intermediate hues that connect them. When comparing the single 1-dimensional line of trichromatic hues to this 2-dimensional spherical monstrum of tetrachromatic hues, you can now understand why functional tetrachromacy is so much more colorful than trichromacy. There's not just a single new hue, but rather an entirely new additional dimension of hue, and each hue can also become more white and black. In a digital number context, trichromacy has roughly 1,500 distinct hues, but tetrachromacy already has more than 1,000,000 distinct hues. And all of these amazing hues and colors can now be seen and differentiated by the mere addition of a single new and distinct range of values. Mathematically speaking, adding a 4th dimension to a previously 3-dimensional system is relatively bland and straightforward, since it's basically just an abstract variable that we are adding. But thanks to these inherently colorful and intuitive visualizations of the tetrachromatic color space, we can give these numbers meaning, uniquity, and beauty. If you were a bit overwhelmed by the sheer amount of true red tetrachromatic hues on the complete tetrachromatic hue sphere, we can also only display the most unique true red tetrachromatic hues with some space in between to better demonstrate their distinctiveness and contrasts. The result is this simplified true red tetrachromatic hue sphere on the right that's populated by the most distinct true red tetrachromatic hues. This visualization allows you to better understand the relations between these tetrachromatic hues. For example, in the center lies the perceptual white of true red tetrachromacy. By drawing a straight line from one hue through the center to the hue on the opposing side, you can easily obtain its complementary hue. For example, the complementary hue of true red black is a black-white hue. The complement of black-yellow is true red-blue, and the complement of true red-green is black-magenta, and so on. For this reason, there's an incredible number of additional contrasts in tetrachromacy, meaning there's another dimension to contrast, thanks to the 2-dimensionality of tetrachromatic hues. And believe me when I tell you that these colors, hues and contrasts are incredible to look at in real life. In fact, I've already seen the Dichoptic versions of almost all of the true red tetrachromatic hues in real life through the true red tetrachromacy glasses, and they truly are incredibly beautiful and incomparable to any normal trichromatic color that I've seen before I became a functional true red tetrachromat. As a side note, I've been using compound color names for these true red tetrachromatic hues so far, but naturally I've already given them all their own names. I'm generally using compound color names because they're easier to understand for and communicate to normal trichromats. If I were to use the actual tetrachromatic color and hue names, you wouldn't know which colors I'm talking about unless I visually showed you, since you don't yet know which color name is associated with which tetrachromatic color. Now, if you were wondering all this time, to the left of this interlaced color view lies the trichromatic view, which demonstrates how these true red tetrachromatic colors look to normal trichromats. Although it may seem like this trichromatic sphere harbors a lot of hues also, many of them are identical and just saturation and luminance variations of normal trichromatic hues. When jumbling up the position of the true red tetrachromatic hues, only a functional true red tetrachromat would be able to solve this puzzle without making any mistakes. In fact, if you want to test for tetrachromacy, you should use such a 2-dimensional hue ordering test design. Any other test may not be adequate and complete enough to fully test for tetrachromacy. We can also unfold and distort this tetrachromatic hue sphere onto a flat planar surface. The result looks like this. This is a simultaneously circular and linear arrangement of tetrachromatic hues. This arrangement perfectly shows that tetrachromacy consists of not just one hue circle like in trichromacy, but rather a continuum of trichromatic hue circles, each containing unique trichromatic hues that together make up the tetrachromatic hue sphere. Unlike in the spherical view from before, this flat planar visualization allows us to see all true red tetrachromatic hues simultaneously by distorting the hue subspace. Here too we can jumble up the tetrachromatic hue plates to transform this flat visualization into a hue ordering test for tetrachromacy. Of course, finding all of the Dichoptic true red tetrachromatic hues as material colors in real life with the true red tetrachromacy classes can become difficult. Even with light colors, it's not as straightforward as it could be because everything man-made is designed for normal trichromacy, and natural lights and reflectances can generally be a bit broad and simple, but tetrachromatic color discriminability thrives on more narrow and complex wavelength combinations. As you can see here, I'm already working on collecting true red tetrachromatic colors as material colors in real life. The colors you can see on this paper are roughly the same tetrachromatic hues as in the flat visualization from before. They are just not completely filled out yet, and you're seeing them through the trichromatic light sensors of my phone camera. There are a lot of true red tetrachromatic hues missing because some of them are very rare in both nature and man-made materials. And when I do encounter these rarer hues, they are often found in light colors or on an object that I, very regrettably, can't just take with me. Now, to conclude, today we've learned that dimensional math doesn't have to be colorless. With a little bit of ingenuity, we can render this kind of math in mesmerizing colors to make it more intuitive and navigable. And we don't need to stop at tetrachromacy and a 4-dimensional color space. With interlaced colors that have 2 components, as well as dichoptic colors, you can build color spaces with up to 6 dimensions. By using interlaced colors with more than 2 component colors, the number of color dimensions can even increase to 9 and 12. But we always have to consider that because we are reusing normal trichromatic colors, with each additional dimension that exceeds trichromacy, there will naturally be some enantiomeric colors. The term enantiomer is borrowed from chemistry, and in this context it describes metameric colors that look the same or very similar when isolated due to the recycling of trichromatic colors, but actually have different virtual cone activations and can look different in a direct context. In true red tetrachromacy, an example of enantiomeric colors is the line of true reds. With dichoptic colors, you can differentiate every hue in this line as a distinct red hue thanks to color context. However, with digitally generated interlaced colors, there's a metameric duplicate of each of these hues on this line. This is why with this approach, the scaling of unique color qualities with each additional virtual recycled cone type becomes less and less effective. Lastly, if you're interested in interlaced colors and want to play around with them, I've developed an application fittingly named Custom Color Vision that allows you to easily integrate interlaced colors into your digital color vision. Although sadly always maximally limited to a trichromatic color space. For example, you can render Minecraft in interlaced true red tetrachromatic colors, albeit always with just one single trichromatic hue circle of tetrachromacy applied. Even with these restrictions, Custom Color Vision is a great and currently the only tool that allows you to play around with and learn to differentiate interlaced colors in real time, among many other functionalities. If you want to support me and get a valuable product in return, you can open the video description and find a link to my app, Custom Color Vision, there. Also, don't forget to support me and my channel by liking and subscribing if you haven't already. I am Oogway, and I will show you how to reshape and enhance your sensory experiences, because it is nothing but our senses that connect us to this world. Have fun watching and learning all these amazing colors. Thanks for watching.